Welcome to our session on symmetry, reciprocal space, and Bloch's theorem. So today we are going to look at what is the role of symmetries in quantum mechanics and in quantum materials, and specifically how we can use symmetries to simplify problems that we will encounter in many of the sessions. As a brief reminder of the previous session, I would like just to mention that we will be interested in Hamiltonians that are essentially written in second quantization. So here you see one of the examples that we've been working on in the previous session, which is a conventional tie-binding Hamiltonian where we have creation operators and annihilation operators, and let's say different matrix elements that correspond to the hoppings. If we want to solve a many-body system for a quantum material, the only thing that we need to do is to diagonalize this Hamiltonian. So we have to make a unitary transformation in this Hamiltonian so that it is in diagonal form, which is the form that you see in the bottom right. Symmetries allow us to do these diagonalizations in a much easier way. Symmetries allow us to find qualitative properties of the solutions of a quantum mechanical problem without actually having to solve the problem explicitly. And that is the motivation for today. We will see how we can use symmetries to just get solutions from of quantum many-body problems and to put constraints on how those solutions can look like. Okay, so to summarize, today we are going to go through several concepts. So first, we'll see that we can classify quantum matter according to the symmetries that it breaks, namely time reversal symmetry, translational symmetry, and others. We will see that symmetry allows us to simplify quantum problems, which is perhaps the most important tool that we will use in the rest of the course. And specifically, that if you think about single particle systems, this symmetry that single particle systems have in the presence of periodicity gives rise to something that you know as Bloch's theorem, which is the fundamental building block to understand electronic structure theory of solids. Okay, let us start with some examples of how symmetry is important. If you look at nature, if you look at, let's say, many different phenomena at many different scales, you actually see that lots of complexity appear. You see this complexity in microscopic systems like liquid crystal. You see this complexity even, let's say, at the scale of the universe in galaxies. And of course, we see this complexity when studying quantum materials. The complexity of physics problems is actually much bigger than what we can usually handle with analytical and computational techniques. So we need to use some tricks. We need to, let's say, learn about the solution of certain problems without actually having to work through every single detail of the problem. And this is where symmetries enter. Symmetries allow us to get global information about a problem without actually having to solve it explicitly. So the basic idea is that in many instances in physics, we may have problems whose solution we cannot find and that they are not analytically solvable. They may be well beyond our computational methodologies and so forth. So symmetries are one technique that allow us to get insight of how this solution is, to put constraints on the solution, and to extract many properties without actually having to work through the details. And that is why it's going to be extremely important for us when dealing with collective states of matter in quantum materials. One can think about, let's say, two different ways of leveraging symmetry. The first one relies on using symmetry as this principle that allows us to simplify problems. This is the essential idea that we will use for systems with translational symmetry to derive Bloch's theorem and so forth. Then there's another idea of symmetry, which is that you may have, let's say, a theory that it's originally symmetric, but whose actual solution is not symmetric. And this is the case of spontaneous symmetry breaking, that it's also an extremely important notion in collective quantum matter. So today we are going to focus on these two cases. So first, how we can use the breaking of symmetry to learn something about materials and the spontaneous breaking of symmetry. And second, how we can use the presence of symmetry to understand something about the solution of some, let's say, complex quantum mechanical problem. Okay, so let us start with the first case. So if you think about physical theories, we very often have let's say, many symmetries. So let's say space is symmetric in the fundamental equations of nature, time is symmetric, and we also have many other symmetries. But if you look at reality, space is not symmetric because, of course, we may have objects in one position and not in another position. Time is also not necessarily symmetric if we have an out of equilibrium system and so forth. So the question for us is why symmetry breaking appears, why original symmetries that appear in our Hamiltonian do not translate onto a symmetry in the ground state. And to understand this, let us start with a very simple example, which is an example that you probably have experienced when going for lunch with your colleagues. So let us imagine that we go to a table, we all sit in the table, we have our plates in front, we have our bread in front, and at some point we need to choose a bread to pick. And you have two options. You have a bread that you can take on your left, you have a bread that you can take on your right. And I am aware that there's a correct choice on this, but if you are me and you're not aware of this choice, then in some cases you may pick the bread on the left, in other cases you may pick the bread on the right. Once you pick one of the two options, then all your colleagues at your size will pick one of the option. And in this problem, there are effectively two solutions. There's the solution in which everybody picks the bread on the left, which is the one that you have on the bottom left of the slide. And there's the solution that everybody picks the bread on the left. That is the solution that you have on the bottom right of the slide. These solutions are, from a physics point of view, let's say, they have the same likelihood. They are equally valid, which in other words means that they have the same energy. So we have a problem that is originally symmetric, but whose dynamics in a way give rise to a solution that it's not symmetric. Each one of these two options differentiates between bread on the left and bread on the right, even though the initial problem didn't. This is an example of symmetry breaking. This is, of course, perhaps a very simplified case, but you can think that this is effectively what happens, for example, in an Ising model. So the idea is the following. So if you consider, let's say, a Hamiltonian for a, let's say, many-body system, so for example, the Hamiltonian of a ferromagnet, you can even think that this is a classical ferromagnet, then the collective, the set of ground states is symmetric. So if you have a solution with all the spins pointing up, you also have a solution with all the spins pointing down. But now, if you have a very, very large system with an infinitely large number of particles, then the system is going to make one of these two choices. So it's going to choose all the spins pointing up or all the spins pointing down. And when you make a measurement, you will only see one of those solutions. Your Hamiltonian was originally symmetric. Your Hamiltonian had initially equivalent solutions, but the solution of this Hamiltonian, each one individually, is not symmetric. And this is what spontaneous symmetry breaking means. And this is something that happens very, very often once you have many body interactions, once you have correlations in a certain material. This idea of symmetry breaking not only appears in magnets, it appears in many other states of matter, and we can actually classify different states of matter according to which symmetries those states break. For example, if you think about time reversal symmetry, which is essentially the symmetry that brings time to minus time, or velocity to minus velocity, or angular momenta to minus angular momenta, then magnets essentially break time reversal symmetry. This is just because the angular momenta that you have in a magnet, the magnetization of a magnet, is odd under time reversal symmetry. Then we can have other broken symmetries, such as, let's say, rotational symmetry or inversion symmetry. This is what happens, for example, in ferroelectrics. So these are materials that they spontaneously develop an electric polarization. You can think that an electric polarization is like an intrinsic electric field. It is the electric analog of a magnetization. And this spontaneous electric dipole essentially breaks the original rotational symmetry in real space of the material. And this happens in ferroelectric materials. And then we have also more subtle symmetries, like the one in superconductors, which is called gauge symmetry. And this gauge symmetry is actually related with the actual phase of your creation and annihilation operators, or if you want to think about it in first quantization, with the phase of the wave function. Superconductors break this gauge symmetry, and many of the phenomena that we observe in superconductivity, like Josephson effect, are related with fluctuations of this symmetry breaking in the phase of the condensate. But we will go through this more in detail in the lecture about superconductivity. Okay, so we've seen that we can classify many states of matter according to which symmetry do they break. They break the inversal symmetry, they are magnet, they break inversion symmetry, they are ferroelectric, they break gauge symmetry, they are superconductor. So now the question is, are all states of matter or all the quantum materials of interest classified according to symmetries that they break? And the answer to this question is no. There are some materials that have unique properties that they cannot be classified according to the symmetry that they break. And these materials are called topological materials. They are called topological insulators. So the basic idea is that you may have materials that have exactly the same broken symmetries, and yet their properties are dramatically different due to them belonging to different topological classifications. And in particular, there's a special kind of topological insulator, which are fractional churn insulators that we will look at more in detail in the specific lecture on topological matter. At this stage, what is important is to note that symmetry breaking is a concept very useful in quantum materials, but there are some states of matter that they escape this classification in terms of order parameters. Okay, so there's one more thing related with symmetry breaking that is extremely important, which is that every time that we have a symmetry breaking, there's the potential for a new quasi-particle to appear. We can have quasi-particles that appear because a material breaks the continuous symmetry of real space. You can think that crystals break the continuous symmetry in real space because, well, you have atoms in one location in space, but you don't have atoms in another location in space. This breaking of the continuous translational symmetry in real space gives rise to a quasi-particle that is called a phonon, that you are already familiar with from the materials physics course. If you have other symmetries, such as the spin rotational symmetry in your material that gets spontaneously broken, then you may have a different type of fundamental excitation, which is called a magnon. So every time that you have a magnet that breaks the inversal symmetry, you also break the SO3 rotational symmetry of the magnetization, because the magnetization is a vector. And this breaking of a continuous symmetry gives rise to this fundamental excitation that we call a magnon. And of course, if you have the breaking of a, let's say, more complex symmetry, such as gauge symmetry, as it happened in superconductors, then we can have a more complex type of excitation, such as the Higgs mode, which is a fundamental excitation that appears in superconductors. Some of the interesting points about these quasi-particles is that they can show properties completely different from the original building blocks of materials that were electrons. So phonons are quasi-particles that have spin 0 and charge 0, and they are gapless in all materials. Magnons are quasi-particles that have spin 1, so in a way they behave as if they were two electrons, but they actually have charge 0. And they can be gapless or gapped depending on the specific electronic structure of the material. And then the Higgs modes, they have, let's say, 0 charge and 0 spin, and they have a gap because of how the free energy of the superconductor is. So symmetry breaking is a very interesting direction for creating emergent quasi-particles that were not present before in the material. Now, how do we know if a certain symmetry is broken? How do we know if a material breaks time reversal symmetry, for example? Well, of course, we cannot just switch the direction of time, right? Time reversal symmetry is not a switch in our lab. We cannot just take that time goes in the opposite direction. So we need to use some other strategies, and the strategies essentially rely on measuring quantities that would change if you switch the direction of time, and in particular, quantities that are odd under time reversal symmetry. And there are two quantities that are odd under time reversal symmetry that are very useful to see the appearance of time reversal symmetry breaking materials. One is the Hall conductivity. That is essentially the conductivity that you observe in a system when you put a voltage in one direction and you measure current in the transverse direction. And then the other quantity or the other measurement is the so-called magneto-optical Kerr effect, which effectively relies on how a material interacts with left-handed and right-handed light. These two techniques allow us to see if a system breaks time reversal symmetry. So we can see if a system has finite magnetization or some spontaneous angular momenta just by doing these measurements. So if the Hall conductivity is non-zero or the magneto-optical Kerr effect is non-zero, then we know that time reversal symmetry is spontaneously broken. Okay, so now let us think a little bit more about magnets, and in particular about these materials that break time reversal symmetry. So the typical way in which we think about magnets is that it is something that somehow attracts some metals. So for example, you can think that magnets are these things that stick to your fridge. But if we want to look for a more mathematical definition, then the way we define them is as objects that break time reversal symmetry, meaning that we have the many-body wave function of a material, and when we apply the time reversal symmetry operator, then the wave function that we recover is different. So, and if this happens, then we say that we have a material that breaks time reversal symmetry. So if we continue with the example of the magnet, what you can actually think is that if you take a magnet that has a north pole and south pole, if you apply time reversal symmetry to it, you essentially switch the poles, because each pole is essentially related with, let's say, the normal to your orbital momenta, and if you switch the sign of your orbital and momenta, then the poles change. If you think about some object that it's not magnetic, like some stick, then if you apply time reversal symmetry, you recover the original object. So if a material is invariant under time reversal symmetry, then we say that it's not a magnet. If a material changes when we apply time reversal symmetry, then we say that in some way it is magnetic. Okay, good. So now let us move on to understand how symmetries help us to, let's say, find solutions of complex problems. So up to now, we have been thinking that symmetries allow us to see which type of material we have, and this is essentially based on the fact that some observables may be zero if we have symmetry, for example, like the magneto-optical Kerr effect or the transverse Hall conductivity. But in the following, let us move on to the case where some specific systems have a solution that respects the symmetry of the original Hamiltonian. And this is, of course, something that you've already seen in quantum mechanics. So when you solve the hydrogen atom, for example, you know that the Hamiltonian of the system has rotational symmetries, and that essentially allows you to find the solution of the Schrödinger equation by factoring out angular and radial degrees of freedom. The angular degrees of freedom give rise to your spherical harmonic. So when you are doing that, you are exploiting symmetry. You are essentially using symmetry to simplify your problem. And of course, the case that it's going to be more relevant for us is the case of periodic crystals. So in a periodic crystal, you can understand that we have a symmetry, we have a transformation that leaves the crystal invariant, that essentially consists on just moving our whole crystal by one lattice constant. This symmetry gives rise to Bloch's theorem, gives rise to the fundamental theorem that we need in order to compute the electronic structure of infinite solids. Now, if we think about the, let's say, the impact of symmetry for, let's say, fundamental excitations, in particular, in the case where we had symmetry breaking, we actually saw that every time that we have symmetry breaking, there's the potential of having new quasi-particles. And these new quasi-particles were the ones that we called phonons or magnons, and we will see that there are several others. This emergence of quasi-particles only appears if we have some spontaneous symmetry breaking, or mostly appears if we only have spontaneous symmetry breaking. In the following, let's assume that, let's say, the symmetry of the solution is the same as the symmetry of the original Hamiltonian. And in this case, we can use symmetries to simplify the Hamiltonian. And this corresponds to the hydrogen atom, for example, and infinite solids. And maybe the most important idea is that if the solution of the Hamiltonian has the same symmetry of the Hamiltonian, then we can factor out our Hamiltonian onto a direct product of Hamiltonians in small Hilbert spaces. So instead of having to solve a problem that it's infinite dimensional, we just have to solve an infinite amount of problems that are finite dimensional. And of course, solving one allows you to solve all of them because they have all the same solution. I think that this will become much more clear once we start looking at some examples. So let us start with simplifying problems using symmetry. So trying to find solutions to complex problems, not by using, let's say, brute force approaches, but actually just by using symmetries to simplify the solution. And this is something that you've been already using in many of the courses before. And maybe one of the, let's say, most well-known examples are the cases in electromagnetism, where they essentially allow you to estimate electric fields, or at least to put constraints on electric fields just from the charge distribution that your problem has. So let us imagine that we have a, let's say, plane with charges, a plane with positive charges, let's say, with a perfectly uniform distribution. And let's imagine that now I ask you in which direction the electric field is going to point. So you have option 1, which is the electric field pointing up. You have option 2, which is the electric field pointing in the left direction. Of course, in this case, we know that the solution is option 1, right? Because if we just apply mirror symmetry, meaning that we just switch left side by the right side, then the problem stays the same, but option two changes. And since the electric field has to be unique, the only solution that is consistent with the problem is the first one. We can look at a problem that may look a bit more difficult. So if you replace your infinite plane just by some elliptical shape that has a uniform charge, in this case, I could ask you the same question. Well, what is the electric field in the x position? So is it option 1 or is it option 2? Here you can use the same trick. You can apply mirror symmetry. Option 1 stays as it is. Option 2 goes from, let's say, tilted to the left to tilted to the right, but the original charge distribution stays the same. So the actual solution to the problem is option 1. So even in the electromagnetism, symmetries allows us to see what the correct solution may look like, right? And of course, before we just focused on mirror symmetry, but we have many different symmetry transformations. If you think about a circle, you have any arbitrary rotation leaves the circle invariant. If you have a square, then 90-degree rotations or 180 or 207 leave the square invariant. If you have some more complex shape, maybe it's only mirror symmetry leaves your object invariant. And when we have quantum system, we can also have, let's say, much more complex and less trivial symmetries that, and this is, of course, what we are going to discuss in the next few lectures. Okay, so now let us look at symmetries a little bit from the mathematical point of view. So if we have a quantum system that is described by a wave function, then to understand symmetries, we just need to understand 3 objects. First, what is our original wave function that is here psi? Then the transformed wave function, which is phi, which is the wave function that we get after applying the symmetry operator. And then we have, of course, the symmetry operator, that is S, that it is, of course, an object that maps one wave function to the other wave function. So if you are working in a vector representation of your wave functions, then S is going to be a matrix. if you think about a very simple case, which is, for example, thinking that your original wave function is a px orbital and that your s operator is a 90-degree rotation, then the orbital that you get at the end is a py orbital. So you start with, let's say, two lobes in the x-axis, you rotate 90 degrees, you end up with two lobes in the y-axis. So a px orbital, for example, is not invariant when you apply a 90-degree rotation. Okay, so now something very important about symmetries is that symmetries are unitary transformations. What this actually means is that when you apply a symmetry to some operator in your Hilbert space, then to some vector in the Hilbert space, then that vector gets mapped to some other vector. But there's a bijection, and in practice, the dagger of your symmetry operator is the inverse of it. And one way of understanding this is that symmetries must leave the norm invariant of any vector in the Hilbert space, because they are just, let's say, a change of perspective in the state. They are just a, let's say, rotation of your axis. So they have to be unitary operators. They cannot change the norm of any vector in real space. So this puts some very strong constraints on which operators can be symmetries in a Hilbert space. And this is going to be very useful when actually writing, let's say, the matrix representation of a symmetry operator. Okay, so now let us look at something very important of symmetry operators, which are its eigenvalues. So originally we looked at a symmetry and a wave function that got transformed into a different wave function. So it was not an eigenstate of the symmetry operator, but we may have actually some wave functions that remain invariant when we apply the symmetry operator. Invariant up to a phase or up to an eigenvalue. So the way to understand this is of course much easier if we look at a specific example. So let us look at this specific example. So imagine that you have, let's say, a wave function that looks like the one that you have in the bottom left. So it's the wave function phi that takes values +1, -1, +1, -1 in real space. And then we think about a symmetry transformation that is a rotation of 90 degrees. And when we do this rotation of 90 degrees, then essentially our wave function transforms into -1, +1, -1, +1. So this transformation, let's say, leaves the wave function invariant up to some quantity. So this wave function is actually an eigenfunction of this transformation. So my question for you is, well, what is the actual eigenvalue of this transformation? And of course, you may very easily realize that it's just -1, because if you just multiply -1, let's say on the left, you essentially get the wave function that you have on the right. You can play this game with a more complex wave function, and actually with a complex wave function. So you can imagine that now you have a wave function that takes values +1, -i, -1i, and then you rotate it by 90 degrees, and all your values change. And now you can ask yourself again, well, what is the eigenvalue of this transformation? If you do it, you will see that the eigenvalue is actually I. So actually, you can have a wave function whose eigenvalue is +1. You can have a wave function whose eigenvalue is -1. Let us look at some other example. So this example is, let's say, less graphic, but maybe a little bit more explicit. So imagine that you have just a top binding model with two sides. So side number 1 and side number 2. And your Hamiltonian is actually just hopping between side number 1 and side number 2. So the Hamiltonian has, let's say, two eigenfunctions, because of course we have just a 2x2 Hamiltonian, and our eigenfunctions are, let's say, C dagger 1 plus C2, C dagger 1 minus C dagger 2. These two eigenfunctions actually get transformed in some way when we apply mirror symmetry. So my question for you is, what is the eigenvalue that we get when we apply mirror symmetry to these wave functions. And of course, mirror symmetry in this system just corresponds to switching 1 by 2. So you can imagine that you have a mirror in the middle between 1 and 2, and this effectively just flips the indexes. If you look at the wave functions, you can very easily see that the first wave function gets a plus, the second wave function gets a minus. So we can have different wave functions picking different signs when we apply a symmetry operation. In general, there's something very important about symmetries and Hamiltonians, which is the following. If you have a Hamiltonian that it remains invariant when you apply a symmetry, which is effectively saying mathematically that S times H times S minus 1 or S dagger is equal to the Hamiltonian, then this actually implies that the Hamiltonian commutes with the symmetry operation. And let me remind you that the Hamiltonian is a matrix in the Hilbert space, and the symmetry is also a matrix in the Hilbert space. So this is actually just a matrix operation. If this condition happens, then every single eigenstate of your Hamiltonian can be an eigenstate of the symmetry operator. And this is maybe the most important idea for today. And the reason for this is because many times it is much easier to classify the eigenstates of a symmetry operator than to classify the eigenstates of a Hamiltonian. So if we know that the eigenbasis of the symmetry operator is the same as the eigenbasis of the Hamiltonian, then we can classify the solutions of the Hamiltonian just by classifying the solutions of the symmetry operator. Of course, the eigenstates of the symmetry operator have a different symmetry eigenvalue than the eigenvalue that they have in the Hamiltonian. But the eigenvalue itself is not important, or at least not the most important part. The most important part is that we are capable of classifying the solutions just by looking at the symmetries that the Hamiltonian have. So in practice, when we start with the Hamiltonian, a very important question for us is to find all the symmetries that the Hamiltonian has. So all the matrices that commute with the Hamiltonian, because by classifying all the solutions of those symmetries, we are effectively classifying all the solutions of the Hamiltonian. And this is exactly what we did in the previous slide, just the other way around. Okay, so in general, symmetry, and in particular, let's say symmetry operators have eigenvalues that, let's say for any eigenfunction. And the most important thing about these eigenvalues is that they always have norm 1, because they need to conserve the norm, and in general, they are complex values. So we can always find that our eigenvalue of the symmetry operation can be written as e to the I phi. So if the eigenvalue is +1, then phi is 0. If the eigenvalue is -1, then phi is pi. If the eigenvalue is something else, we may have, of course, let's say a finite phi that gives rise to a complex number. Okay, very good. So now let us do some, let's say, very small exercise. So let us imagine that we have this Hamiltonian. This is the Hamiltonian of a tie-binding model with 3 sides, right? And this Hamiltonian of a tie-binding model with 3 sides has a symmetry, which is 120-degree rotation. So my question for you is, what are the eigenvalues of the symmetry operator of this Hamiltonian, which are the rotation? So in practice, I'm asking you, what are the possible values of phi for the eigenstates of this Hamiltonian? You can think for a few seconds about it. And after thinking about it, you will realize that the eigenvalues are actually very simple. So if you rotate 120 degrees 3 times, you recover your original system. What this actually means is that applying rotation 3 times returns the identity, which effectively means that your eigenvalue to the 3rd power must be 1. And you can think about all the complex numbers with this property. And after thinking about them, you will see that, well, the complex values with this property essentially have a phase that is 2n pi over 3 with n 0, 1, 2. So with this, you actually know what are the, you have already a lot of information about what are the eigenstates of your Hamiltonian. So let us try to look at them more in detail. So in general, the eigenstate of a Hamiltonian for three sides is going to be alpha 1 C1, alpha 2 C2, alpha 3 C3, with alpha I a specific complex number. So now what I would like to ask you is what are the coefficients, alpha 1, alpha 2, and alpha 3 of this wave function for the eigenstates of the Hamiltonian? To answer this question, you just need to realize that when you apply the rotation operator, you are essentially switching 1 to 2, 2 to 3, 3 to 1. And what we said before is that the phase that our wave function is going to pick is quantized and is this phase that is 2n pi over 3 with n equal to 0, 1, and 2. So with that, you can actually see that the phases that you get in the coefficients are going to be exactly the phases that you have in the rotation operator. So you can directly find the eigenfunctions of the Hamiltonian just by looking at the symmetry that the Hamiltonian has. Let us look at a, let's say, slightly more complicated problem. So let's imagine that instead of having 3 sides, you have 5 sides. And these 5 sides have, let's say, first neighbor hopping. So you have a first neighbor tie-bonding model. And now I'm asking you again, well, what is the symmetry eigenvalues that this Hamiltonian has? You can very easily see that this is just the generalization of the previous problem. So instead of having, let's say, 2n pi over 3, you will have 2n pi over 5. And if I now ask you, well, what is the actual value of the previous, of the correlator that you see over there? So C1 and the lowest energy state dagger over the empty state, then you can very easily see that this is actually going to be 1 over 5, because of course this is a model with 5 sides. So in this way, you can actually guess both the wave functions and some expectation value just by looking at the symmetry of the Hamiltonian without actually having to do any calculation whatsoever. We can play the same game even with a more complex Hamiltonian. So even if instead of having first neighbor hopping, you have, let's say, some long range hopping, then even though the Hamiltonian is more complex, the symmetries are essentially analogous. So we can find the symmetry eigenvalues, we can find the eigenfunctions themselves, and we can find also the expectation values just using symmetry as a tool. Okay, so of course, many of these models may look like, let's say, maybe not realistic or not very relevant for materials, but what is important to note is that these models with a few sides, they can actually be done in the experiment, and they can be done very, very efficiently using scanning tunneling microscopy. And in particular, there's a very famous example, which is actually a movie that was built by moving atoms on a surface. So every single dot that you see in that image is an actual individual atom. And you can see a very beautiful story of a kid playing with his atom. And this is actually the smallest film ever created by humankind. So these models using a few sites, they can actually be realized experimentally, and they will be relevant later on during the course. Okay, let us now move on to maybe the more interesting example of symmetry, which is the case of an infinite dimensional problem. Let us imagine that we have a chain. Okay, so now instead of having a finite number of sides, we have an infinite number of sides. And we have first neighbor hopping, just to simplify the problem. This chain has a very obvious symmetry, which is what we usually call translational symmetry, which means replacing every Cn by Cn plus 1. This is just a transformation in the Hamiltonian. And you can see that this transformation commutes with the Hamiltonian. What that actually means that there's a common basis for the Hamiltonian and the symmetry operation. In other words, we can find eigenstates that are simultaneously eigenstates of the Hamiltonian and eigenstates of the symmetry operation. And of course, those eigenstates pick a certain, let's say, eigenvalue when the symmetry operation is applied. And that eigenvalue is, of course, a complex number, and it's to the e to the I phi. The parameter phi in this symmetry eigenvalue is what we are going to call the Bloch phase of the wave function. So Bloch's theorem is just saying that if two operators commute, there's a common basis for both of them. Okay, so now the basic idea is that we can classify the eigenstates according to the phase that they pick when we apply translational symmetry. This actually means that the energies of those eigenstates when we apply the Hamiltonian can also be classified according to the phase that their associated wave function has. So there's a mapping between the phase that an eigenstate gains when translational symmetry is applied and the energy of the state. So the phase is related with the symmetry eigenvalue, and the energy is related with the eigenvalue of the actual Hamiltonian. So effectively, this mapping between the phase in the symmetry and the energy is what we call the dispersion relation of a periodic system. And this can be done in a, let's say, more mathematical structured way. So let's imagine that you have your original Hamiltonian that is written in real space, so just a one-dimensional tie-binding model with first neighbor hopping. And we know that this Hamiltonian commutes with translational symmetry. What this actually means is that we know that the eigenvectors of this Hamiltonian must pick a phase when you apply translational symmetry. So our objective here is to find a diagonal basis for this Hamiltonian. So the way we do is we essentially assume that our eigenstates can be written as a linear combination of our creation operators, which is, of course, how the eigenstates are going to look like. And then we define the coefficients in such a way so that they pick a phase every time that we translate by one side. If we just use this definition of the coefficients that you see on the right and plug it onto our definition of the eigenstates and plug our eigenstates in the original Hamiltonian, you can actually see that you can directly find the mapping between the eigenstate of the Hamiltonian and the phase, and this mapping corresponds to obtaining that the energy is 2 times the cosine of the phase. This is just applying this simple notion from linear algebra to a one-dimensional tie-binding model. The dispersion relation of a one-dimensional tie-binding model is simply 2 times the cosine of the phase. And this is something that we could do just because we knew how the solutions look like. We didn't have to diagonalize an infinite dimensional problem. We just had to realize that the solutions actually had this symmetry in which they pick a phase every time that you go from n to n plus 1. Okay, so you actually can perform many of these calculations, not only analytically, but also doing computational packages. And in particular, there will be one that we will use during the some of the lectures during the course, which is called Picula. And this will allow us to compute the band structures of one-dimensional systems, two-dimensional systems, three-dimensional systems, and so forth, and doing also many other things. But we will go through this more in detail in some of the next sessions. Of course, you can apply, let's say, this Bloch's theorem or this translational symmetry every time they have a periodic system. You don't need to have a single site per unit cell, but you can have 2 sites per unit cell. And if you have 2 sites per unit cell, instead of having one eigenvalue for every phase, then you have 2 eigenvalues for every phase. So instead of having 1 band, you have 2 bands. And this is, of course, something that we will also do computationally. Now, of course, in many cases, we are not only interested in one-dimensional systems, but we also want to compute 2-dimensional systems or 3-dimensional or even higher dimensional. If you have a 2-dimensional system, the idea is very similar as in a 1-dimensional system. So instead of having just one symmetry, which is the translational symmetry in one direction, now we have 2 translational symmetries, one in the x direction, one in the y direction. And these 2 symmetries are completely independent. Your Hamiltonian commutes with both of them, but the two of them are completely independent. So your wave function is going to pick a phase when you apply one of the symmetries, for example, translation in X, and your Hamiltonian is going to pick another phase when you apply the other symmetry, for example, translation in Y. So effectively, your phases are going to live in a two-dimensional space, so a two-dimensional square that goes from 0 to 2 pi for phi x and 0 to 2 pi for phi y. And this two-dimensional space is what it's called the Brillouin zone. So when you think about the Brillouin zone in, let's say, actual crystals, what you are actually thinking about are the symmetry eigenvalues of the symmetry operators. And of course, this, let's say, two-dimensional space for the phases is not, let's say, an infinite space, but it's a compact space, because 0 and pi are effectively the same phase, and 0 and 2 pi are effectively the same phase, both for phi x and for phi y. So your actual square is wrapped. You need to identify the bottom and top lines and the left and right line. So your Brillouin zone is effectively a torus for a two-dimensional system, and for a one-dimensional system is effectively a circle. Okay, so this is maybe the most important concepts that we need for today's lecture. So maybe the things to remember from this lecture is that symmetries allow us to classify quantum matter, and we can learn a lot about the properties and the potential emergence of quantum many-body system just by thinking about which symmetries the system breaks. And then the second important point is that symmetries allow us to simplify quantum problems, and in particular, for single particle systems with translational symmetry, we can solve the whole Hamiltonian just by mapping the symmetry eigenvalues to the Hamiltonian eigenvalues, and this is what we usually call electronic structure theory. So thank you so much for your attention.